So, what I want you to take a peek at, I had you grab your book, and what I want you to do is open up to about page 520, 520. 520. Okay, but before we get too far, on page 521, okay, that concept that we see on the bottom of page 521, I can't illustrate or can't stress enough how important that is. Why do you suppose there's 8 columns there? And we've talked about it, but in an indirect manner. How many columns do you see on the bottom of page 521? There are 8 of them. So what we see happening is, remember, we can make certain predictions about how many electrons are in an outer energy level by noticing what column it's in. Okay? So on any one of them top rows, okay, not hydrogen or helium, but any one of the other ones. Go ahead and pick one of them. Boron. Is that because it sounds like boring? Or moron? Moron the boron? Boron the moron? So if you call someone boron, you actually mean moron. Okay, fair enough. Okay. So, what we're illustrating then, okay, is something like this. You said boron. So what can you tell me about the element boron other than the letter B? Why is 5 important? That tells you how many protons you have. What else can you tell me about boron? Okay, that's another prediction that you can make. So does it give you atomic mass? No, it doesn't. So I think it's approximately, is it 11 maybe? We're going to call it 11. What can you tell me about neutrons for boron? There's 6 of them. Why are you right? That's right. Okay, so if we're going to do these energy levels, okay, there's a couple predictions that some of you pointed out already. So what period is boron in? Don't get columns and periods mixed up. Those are 2 different concepts. No. It's in the second period. What column is it in? Okay, so the numbers 2 and 3 are significant. So if we're going to put, what is this telling you? We're in the first energy level. And what block is first? S, which means it can hold how many? And we're going to put both of them in there. Okay? Then the slide rule goes on to tell you what? Okay? So that big number 2 is important because it tells you another energy level. And again, we made the prediction. What period is boron in? The second period. Okay? Oh, okay? So I don't know if I'm coordinated enough to periods and columns. I can't go straight across like this and straight up and down. Maybe I'm just, I can't at the same time. Am I just that uncoordinated, or? But you get the idea. Okay. So it's in the second period. Okay? So that means it has 2 energy levels. Well, we've got the 2 here. So your slide rule is telling you what as we proceed? Okay? And then once we get past this into the P block, remember it can hold 6. But we're only only going to put 1. Okay? Well, okay, so there's a couple of reasons why. The 1E, because it's in the first column of the P block. There's 3 total because it's in the third total column. Okay? So we're hoping that we're starting to catch this pattern. We can't make this intuitive leap with D block elements. Well, you can, but you got to be careful. Because what did we mean by N minus 1? For instance, elements like scandium all the way up to zinc. We know that those are transition metals. They're in the D block. But what energy level is that? 1 less, so that's important. What period does it look like it's in? Elements 21 to 30, it looks like it's in which period? It looks like it's in the 4th one, but it's not. It's actually the what? The 3rd. That's why that N minus 1 is so important. Okay? So just as a quick review, we can look at cobalt. Okay? Because that's an example. Okay? Element 24? 27. Okay. 27. So again, we can do this. 1s2, then what? 2s2, 2p6, 3p6, and this is where that N minus 1 is associated. Now, when you look at the D block, what column is cobalt in? Okay, so when we add all these numbers together, we should get what? 27. Okay, so that's what we mean. You got to be careful if you're making those predictions. You could say, well, yeah, it's in the 3rd period by saying N minus 1. That's why you got to be careful. You don't want to say it's in the 4th period. And your slide rule tells you that. Okay, and for all these energy levels, okay, if we're looking at the first one, it can hold 2. The second one can hold 8. The third one doesn't hold 8. It actually holds how many? That's what it's telling you on page 520 instead of 521. What does the third one actually hold? Someone said it. 18. Okay, so how do we get in that number from 8 all the way up to 18? Why is that so random? Because there's something about the number 10. What was that? There's 10 columns in that D block. Okay? So once we get up to the 4th energy level, do you think that that is 18 as well? No, it's 32. Well, why are we making that jump from 18 all the way up to 32? How did we get up to there? Something significant about the number 14, and that's which block? The F block, that's right. The 5th one can hold 32, then it starts to go back down again after you get past the 5th energy level. Okay, so keep in mind energy levels, okay? You can illustrate that by the periods, but you got to be careful, especially with these D block elements, okay? If it's an S block or a P block element, you can make that prediction, okay? So, how is this Bohr model going to be different than an electron configuration? Written? Yeah, it's a linear depiction. It means it comes out in a line. So, we've never done one the long way with a big element. We've always taken a shortcut. Is there any reason you would want to see how to do it the long way? Probably not. Okay? So, if we're taking the shortcut, which we can, we have to use specifically which noble gas? You're right. Why are you right? The next smallest one, okay? Because remember, this is 27. We can't go up to 36 with krypton, but we can go down to 18 with argon. Okay? So therefore, we're up to 18. So now, what period is argon in? The third. What column is argon in? The 8th or the 6th, depending which way you look at it. So on your slide rule, what comes after 3p6? 4s2, and then what? It would be 3d10, but remember, what column is cobalt in? The 7th one. Okay? So what happens when you add 2, 7, and 18? You get 27, and that's what we're looking for. So the ones that are left over are this one and this one. This is where they're coming from. That 4th energy level, 1, 2, 3, 4. There it is. The 3rd energy level, there were 7 of them. There it is right there. Oops. Put that in there. 3d7. Okay. If there's any confusion, are we closing that gap? Middle. Are we good? Okay. Left outside. Okay. Right middle. Okay. Left middle. Right outside. Right outside. Right outside. Right outside. Yes? Right outside. Okay. So we're going to find out probably on Friday. I'm going to push that problem quiz back a day. The next thing I want to look at very quickly, page 522. What do you notice about figure 12? What is it trying to illustrate? What's true about hydrogen, lithium, sodium, potassium, rubidium? Why is there always just one dot next to them? Because it's in the first column. Okay? So, what is a valence electron? In the outer energy level. So, if we were to back up one page, remember we said boron is in column 3, right? So if that's the case, how many valence electrons does it have? 3, right? So remember, the column that it falls in for S and P, that tells you how many valence electrons it has. And that's why you see hydrogen, sodium, potassium, rubidium, and cesium all having one dot because it's in the first column. It has one valence electron. The last thing I want to point out is on the bottom of page 522, they're showing you what we call electron dot diagrams. Even though that's in this chapter, we are not going to cover that until next chapter. Okay? And there's a reason for that. Because we've gone over enough materials to why throw this in here. And what we mean by that, it's, for instance, like trying to pour a gallon back into a liter. Which one's bigger? A gallon or a liter? Okay? So the human cranium, see, I can, skull is actually, the cranium's actually pretty durable. It just hurts, that's all. But anyway, so with that, this human cranium, let's say, holds probably maybe one, I'm just going to say 1.2 liters. So if we take a gallon, working so hard, need a drink? Yes, that's fine. So next to that humidifier, there's a gallon. Okay? If you take that gallon and dump it into here, what's going to happen? It's going to overflow. So at what point do we cut things off? I think the appropriate answer is Bohr models and configurations. That's enough information for this chapter. Because if we start pouring these electron dot diagrams in here, it's about like pouring this into your cranium, and all that information's not going to stay. Well, for some people it might, but it's just going to overflow. Does that make sense? Okay? else, we can just say, no, we need to do them, or else I can't sleep at night. Somebody thought that was funny, and I would agree, because we just told a funny, didn't we? Okay. Ha ha. Two, element two. You get it, don't you? Who does not get that? Now be honest. Why would we say 2? Look up the periodic table. Helium, which the symbol is He. So he. We could also say hafnium and wolfram too, or tungsten. Hafnium is Ha, and tungsten is W. Ha. He ha. See, and I sometimes talk about this with other classes. Some of you are smiling and laughing. Did you break your face? No, it's one of them things. Your face is not going to break if you smile. Okay? Otherwise, it just looks like we're so angry that we got to sit through this and listen to he, ho, ha. So we try to make this somewhat exciting. Okay. One of the things that we left off with, okay, and that was when it comes to munitions is a pretty vague term. What do you suppose munitions means? It can. So I believe anything that will ignite or explode or something to that effect. I think it was actually over Christmas break, or was it Thanksgiving break, there was a chemical plant in Texas that had actually caught fire and had to actually evacuate the town. I want to say that was over Christmas break. And sometimes these industrial accidents do happen, and with unfortunate, terrible results, because sometimes some of these compounds, they actually become so unstable that they do explode from time to time. Okay, so in this case, we left off with this chemistry expert, and they actually do what's called a chemical analysis on this. And I don't know if they're using what's called a gas chromatograph or a mass spectrometer. So what they do is inject a sample of this, and at the atomic level, laser beam shoots through there, and as that laser beam is refracted, it tells you how big those elements are. And that's how you determine what's in a substance. Okay? And it gives you somewhat of an idea. So when atoms ignite or explode, diesel fuel, gasoline, or you can say are kind of mild mannered, because that's when the internal combustion engine is. When those molecules break apart and recombine again, that's where you get your energy from. Okay? And that's what they're going to be illustrating here shortly. So we'll continue with this video. Now wait till later to put these books back.